Welcome to The Explainer. Today, we are diving right into the nuts and bolts of building a PyTorch binary classification model, literally from scratch. And we aren't just looking at abstract math here, we're actually going to build a diagnostic engine to predict whether or not a patient has diabetes. So if you've ever wanted a super clear under-the-hood look at a complete machine learning workflow, you are in exactly the right place.
Okay, let's take a quick look at this assembly line workflow. First, we'll set up our data, then build the actual PyTorch model and power through a 10,000 epoch training loop. After that, we'll evaluate the performance, diagnose a brand new patient, and finally, it'll be your turn to practice. This should give you a really solid mental blueprint of how we go from raw data to a fully trained tool.
All right, let's kick things off with Section 1, setting up the data, also known as our materials gathering phase.
Now, before we write a single line of logic, we've got to check our tools, right? For this explainer, we are running PyTorch version 2.5.1. Our essential kit includes pandas, which we use to load our Pima diabetes dataset from a CSV. In this data, each row is one patient, and our target column is outcome, where a 0 means no diabetes and a 1 means they do have it. We're also using scikit-learn to split and scale the data, while PyTorch, the star of the show, handles our tensors and trains the actual neural network.
Once that data is loaded, we split it up using scikit-learn's train-test split, holding back 20% for testing later. But here is an absolutely crucial detail: the stratify parameter. Stratifying prevents our model from accidentally training on a weirdly skewed dataset. It guarantees that our training set and our test set both maintain the exact same ratio of class 0 to class 1 patients. That keeps everything representative of the real world.
So our final data prep step is incredibly important. You see, we can't just hand a raw pandas data frame over to PyTorch and expect magic. Neural network optimizers rely on really stable math. So first, we use scikit-learn's standard scaler to smooth out our features, which makes the model weight updates much smoother later. Then we convert those scaled arrays into PyTorch float32 tensors, because PyTorch absolutely requires these multi-dimensional arrays for its heavy-duty calculations. Oh, and we also reshape our labels into a single column so PyTorch can read them properly.
Moving right along to Section 2, building the PyTorch model. Let's look at the actual machine construction.
In PyTorch, we build a binary logistic regression model using nn.linear. But what exactly does that linear layer spit out? Well, it gives us something called a logit. A logit is basically the raw, unscaled numerical score from our linear equation z equals w times x plus b. So our model's output isn't a neat percentage yet, it's just this raw score. A big positive logic means the model is leaning hard toward class 1, or diabetes, and a big negative logic leans toward class 0.
But how does the model actually know if that logit is any good? For that, we need a loss function. Since this is binary classification, we use BCE with logit's loss. BCE stands for binary cross entropy, which measures how wrong our predictions are and heavily punishes confident but incorrect answers. Now, pay close attention here. This function automatically combines the sigmoid function, which turns those logits into actual probabilities, and the cross entropy calculation into one perfectly stable step. So do not apply the sigmoid function manually before passing data to this loss function. It's a really common trap.
All right, on to Section 3, the 10,000 epoch training loop. We are heading down into the engine room now.
Before we fire up the loop, we have to set up our optimizer. We're going with SGD, or stochastic gradient descent, with a learning rate of 0.01. This number is like a dial. It controls exactly how large of a step our optimizer takes when adjusting weights. If it's too big, the model just overshoots the right answer entirely, but if it's too small, we'll be sitting here forever waiting for it to learn.
And here's the beating heart of PyTorch training. I like to think of this like a student studying. Step 1 is the forward pass. The model takes a practice test and calculates its logits. Step 2 is calculating the loss, basically checking the answer key to see how badly it did. Step 3 zeroes the gradients, which wipes the scratchpad clean. Step 4 is backpropagation, figuring out exactly where the math went wrong. And finally, Step 5 is the optimizer step, where the student actually updates their internal knowledge base, the weights and the bias.
Now, our model repeats this exact study cycle for 10,000 epochs. It sounds like a massive number, right? But we picked it because this particular linear model needs that time to iterate. Over these 10,000 passes, we can watch the binary cross-entropy loss gradually drop. In fact, it drops down to a highly stable 0.4662 right around epoch 6900, and basically just stays there. which tells us the model has learned all it possibly can from this setup.
Section 4. Evaluating performance. Time for some quality assurance on our newly trained model.
Training is officially done, so we turn off gradient tracking with torch.nograd to save memory and bring in that unseen test data. Now, since we aren't using that combined loss function anymore, we actually do have to manually run our raw test logits through torch.sigmoid to get probabilities between 0 and 1. Once we have a probability, the rule is super simple. If it's exactly 0.5 or higher, the model predicts diabetes. Below 0.5, no diabetes.
To see how we actually did, we flatten our PyTorch prediction tensors into a standard NumPy array and compare them to the true test labels. Overall, our model hit about 71.4% accuracy. Not too bad. Looking at the confusion matrix, it successfully identified 82 true negatives and 28 true positives, though it did slip up with 18 false positives and 26 false negatives.
We can zoom in even further with the classification report, which breaks things down by class. If you look at the recall column, you'll notice the model is actually really solid at ruling out diabetes. Class 0 recall is a strong 0.82, but it definitely struggles a bit more with finding all the positive cases, sitting at just 0.52 recall there. This is great info because it tells us exactly where the model is strong and where we'd want to tweak things in the future.
Section 5. Diagnosing a new patient. Let's put this pipeline to the ultimate test.
Imagine a real-world, high-stakes scenario. We have a brand-new 35-year-old patient waiting on a diagnosis. They have a BMI of 32.0, glucose of 130, and so on. We drop this data into a pandas data frame. And critically, we have to apply the exact same standard scaler to this new patient that we used during training, and then convert it right into a PyTorch float32 tensor.
The data is perfectly prepped. We feed these scaled tensor vitals through our binary model, calculate the raw logit, and run it through torch.sigmoid. So, moment of truth here. Does this new patient have diabetes?
The math resolves, and the model gives us a predicted probability of 0.318 for class 1.
Remember our simple classification rule? Because 0.318 is strictly below our 0.5 threshold, the patient is classified as a 0. The model predicts no diabetes. And just like that, we've executed a fully successful end-to-end machine learning pipeline.
Finally, Section 6. Your turn to practice. Time to apply what you've learned.
We built this assembly line together, but, watching me do it is only half the battle. The source material for this explainer actually provides an awesome practice data set dealing with customer churn. You get monthly usage hours, support tickets, things like that. Your mission is to use the exact same binary classification pipeline we just built to predict if a customer is going to cancel their service, which is class 1, or if they'll stay, which is class 0.
It is quite literally the perfect way to solidify all these PyTorch concepts in your brain. So as you go tackle this new problem, I want to leave you with this provocative thought. Knowing how everything in the engine room interacts, how will you tune your learning rate and your training epochs to build an even more accurate model? Will you just go for 10,000 passes again, or adjust your optimizer's step size? Get in there and find out. Thanks so much for joining me on this explainer.